Hi, so now we're going to talk about some more stuff with tangent lines. So here we have a circle, circle A. Remember, circles are named for their center. This is the tangent line, tangent at point B, and B we know is called the point of tangency. Okay, so there's your point of tangency. So a line can be tangent to a circle. We could call that a segment. Segments can be tangent to a circle. Even two circles can be tangent to each other as long as they only kind of touch at the one place. So circles can be tangent this way, circles can be tangent this way, maybe the circle's inside the other one. Lots of different versions of that can happen. Other things that we can say are that we have tangent circles, here we go, or internally common tangent lines. So that would mean, so here's the internal space in between these two circles. So if we wanted to draw a tangent line in between them, that is one tangent line and it crosses through this internal space. So this is a line that we can say is internally tangent, because it's in here, and it's common to both of these. So that is one example. We can also draw this example here. So there's another line. It is tangent to both. That makes it a common tangent, and it crosses through this internal space. So that's why it's internally common tangent lines. Okay, so now we want, again, common tangents. So it has to be tangent to both circles, and externally, which means we are not going to cross through this inside space. So one of our lines will look like this. There's that. And our other line is going to look like this up here. Okay, so these guys tangent here, 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 and it stays in the external space. It's not here in the internal space. So moving on. That's just kind of some visual pictures. What we really want to do is work on a couple of these theorems or rules, because this is where everything kind of comes into play. Sorry, I kind of messed that up. Okay, so here we go. If a line is tangent to a given circle, then here at point B, at the point of tangency, there is a perpendicular line that we can draw from the radius. Okay, so what happens here is if you have a line that you know is tangent to a circle, so tangent line, then, that's the if part, then we know that it's perpendicular to radius. So that tangent line is perpendicular to the radius. Of course, the radius that goes from the center to that point B, which is the point of tangency. Okay, so let's see how that can happen over here. Now, by the way, as soon as we have this right angle here, enter all of the right triangle problems. So lots of right triangles coming now. So we are given that BD is a tangent line. B is our point of tangency. We have circle A, right, named for the center. And we know the radius is 5. They wrote it in here. And this segment here is 12. As soon as they tell us we have a tangent line, we can draw in this perpendicular. Now I know I have a right triangle. A squared plus B squared equals C squared. Call that C. So 5 squared plus 12 squared is equal to C squared. You can do the math with your calculator, or maybe some of us have this memorized, and we know that this is a 5, 12, 13. So this hypotenuse is 13, but that's not what they're asking for. They're asking for what ED is. ED is this outside space. So this will happen sometimes too. So finding this piece of a segment is kind of too hard, so we're not going to do that. Instead, we found the entire segment, but remember, these are radii. And all of the radii in the same circle are congruent to each other, so that piece is 5. If this piece is 5, the entire thing is 13, well then this piece over here must be 8. So ED is equal to flip over. Let's do a couple more. So here we have on the back, same thing. We are given that we have a tangent line. As soon as we have a tangent line, perpendicular. So I see this one here. Looks like they only give me this one measurement, 4, but they mark all 3 of these pieces the same, meaning this is 4 and this is 4. So in my right triangle, I don't know my hypotenuse and AT, that's actually what I'm looking for, but this side is 4 and this side, 4 plus 4 is 8. So 4 squared plus 8 squared is equal to C squared. 16 and 64, that's 80. You could do this in your calculator, but I know that square root, that 80 is 16 times 5. So I take the square root of each of those numbers, and 4 square root of 16 is 4, and I cannot take the square root of 5, so 4 radical 5 centimeters. Did I have measurements on the other side? I did. Centimeters, sorry. Okay, C, or 3, circle C. So in circle C over here, I have this one side, and they don't give me the other sides, but they say that they're all the same, so I'm just going to call them all X. So if I know this is tangent, then I have this right angle, and now I can do the Pythagorean theorem. Looks like I don't have 2 sides, but at least there's only one variable here. So I have my one side, x squared, my other leg, plus 7 radical 3 squared, equals, well, x plus x is 2x, right? So then that's 2x squared. X squared plus, all right, so now when you're squaring things, if you're multiplying, we're squaring each of those numbers. So that's 49. And then radical 3 squared is 3. 49 times 3 is 147. Same over here, we're squaring each of these numbers. That's 4x squared. Minus x squared to this side. 3x squared, get the x alone, divide by 3. Well, 147 divided by 3 is 49, equals x squared. Take the square root. That'll work. X is equal to 7. So, at least it worked out nicely, right? 7, 7, 7. So coming down to my answers, CB, that's the radius, that's 7, and AC is 7 plus 7, that guy here is 14. Measurements, so I'm going to move on. Okay, so this last thing over here is the converse. Okay, so let's go up here. We said, hey, if tangent, that means it's perpendicular. So now what we are going to do is go backwards. And we're going to say, well, if it's perpendicular, then you know that it's a tangent line. So if perpendicular, right here, so if it's a right angle, then tangent. So for number 4, is it a tangent line? Well, if you want to know if something is tangent, then you must have perpendicular lines, or these 2 segments here. You have to have that right angle at a point of tangency. So looking at number 4, if this here is a right angle, then the line is tangent. So we are still using our Pythagorean theorem. We're going to test with a squared plus b squared equals c squared. And if the Pythagorean theorem holds true, then we know that we do have a right angle here, and when we have the right angle, then we know the line is tangent. So let's see. So they more or less have to give you all the sides so that you can plug it into the Pythagorean theorem. So we have one side here is 4, this side here is 3, and it doesn't look like they give us this entire hypotenuse. We would assume that's the hypotenuse. We want to put the right angle there. But we know this piece is 2, and that's a radius. Radius is all the same. Make that 3. So now 3, 4, and 5 are the sides of this triangle. 3 squared, 4 squared. You want to know if it's equal to 5 squared, and you know what it is. It's a 3, 4, 5. So then yes, is it tangent? Yes, it is. Because we just showed that this is a right triangle. When I move on to number 5, Let's check this one out. It's kind of the same setup where they give us the radius and this external segment length here. This piece is 3. Well, I know that this is 6. If it's a right triangle, the right angle has to be here, making 6 and 8 my 2 legs. So those are my A and my B. So when I try the Pythagorean theorem, squared b squared plus c squared, 6 squared plus 8 squared, we want to know if it's equal to 6 and 3 is 9 squared. 36 and 64, well that is 100. Oh, and on this side it's 81. And these are not equal. So since a squared plus b squared is not equal to c squared, it is not a right triangle, so that is not perpendicular, that's not a right angle. This is when we did like the greater than less than, acute obtuse. We don't need to get into that right now. We just want to show whether it is going to work and that it is a right angle, it is tangent, or if it's not. That's how those are going to work.